Today, we're going to talk about the single biggest piece of hardware that made our current AI moment possible. And, the story starts in a pretty surprising place, not in some high-tech research lab, but in the world of video games.
Okay, so let's get right into it, because this is the central mystery, right? The basic ideas behind neural networks, the blueprint for an AI's brain, they're not new. I mean, they've been around for decades. So what was the missing piece? Why now? Why did we have to wait all this time for stuff like ChatGPT?
And there it is. That's our answer. The bottleneck was never a lack of brilliant ideas. It was a lack of pure, raw, computational horsepower. The algorithms were sitting there ready to go, but our computers just couldn't handle the workout. To really understand that bottleneck, we've got to zoom in on this one mathematical operation that is, quite literally, the beating heart of every single neural network. For decades, this one thing was like hitting a brick wall for AI progress. It's called the matrix multiplication problem.
So what is matrix multiplication? Okay, imagine you have a giant spreadsheet with patient data. Each row is a different patient. Each column is something like blood pressure or cholesterol. A neural network works by taking that entire table of numbers and multiplying it by another table of numbers, which we call weights. And it has to do this over and over and over again. Let's look at a really small-scale example, just to make it real. Say we've got 100 patients, and we're tracking 5 things about each of them. We want to run this through a tiny little layer of our AI that has just 4 neurons. Well, that means we have to multiply our 100 by 5 patient table with a 5 by 4 weights table. Even for something this small, the number of calculations is surprisingly huge. Now, for the longest time, computers used their main brain, the CPU, to do this kind of math. And a CPU is a very orderly worker. It works sequentially. So it calculates the answer for the very first cell. Once that's totally done, it moves on to the second cell, then the third, one by one, step by painstaking step for all 400 cells in our final table. So here's where it all breaks down, the cost. Using this one-at-a-time method, our tiny example would take about 2,000 units of time. Now remember, a real AI model is doing millions of these, with tables that are thousands of times bigger. You can see pretty quick why this was a total dead end. It was just way too slow. But then, researchers stumbled on a solution, and it came from a totally unlikely place, the Graphics Processing Unit, or GPU. Yep, the chip that was designed to make your video games look incredible. And it turns out it had a secret superpower that was absolutely perfect for AI. You see, the difference between them is really a difference in philosophy. A CPU is like a specialist, a master chef maybe. It's designed to do a few really complex things very, very well, one after another. A GPU, on the other hand, that's like an army. It's built to handle thousands upon thousands of simple, repetitive tasks all at the exact same time. So instead of seeing one big, long task, a GPU looks at our problem and breaks it down. It sees that calculating each of those 400 spots in our final table is its own little independent job. And in the world of GPUs, each of those little jobs has a name. It's called a kernel. And this right here is the whole game changer. The old CPU way was like having one person do 400 jobs in a row. The GPU way is like having 400 workers and giving each of them just one job to do. They all start at the same time, and they all finish at pretty much the same time. This is what we call parallel processing. So what's the payoff? Well, remember the CPU took 2,000 units of time? The GPU, by doing everything all at once, takes just 5. 5! The time it takes for just one of those little calculations to finish. That's a 400 times speed up on our tiny problem. On real-world AI models, the difference is just astronomical. So, what did this all mean? Well, applying a gaming chip to a math problem, that's what finally blew the doors off AI research. It was the moment that all those decades of theory could finally be put into practice at a massive, world-changing scale. And this timeline really tells the whole story, doesn't it? The ideas were there for decades, just simmering. Then, in the early 2010s, researchers really started adopting GPUs for this kind of work. And just a decade later, we get an absolute explosion of generative AI. The hardware finally caught up with the ambition of the software. But as always, you solve one huge problem and it tends to create a brand new one. And in this case, by solving the computation problem, we've created a whole new set of massive global challenges.
The success of the GPU has pushed us into a new frontier where the bottlenecks aren't just mathematical anymore, they're physical.
And we're not talking about small hurdles here. We're talking about monumental challenges. Running millions of these powerful chips eats up an unbelievable amount of electricity. We're talking as much as entire countries. All that electricity generates an insane amount of heat. This has kicked off a global scramble for rare earth materials that can handle the temperatures. And all of a sudden, the big conversation around AI has become about geopolitics and renewable energy. The new race for AI dominance is a race for power, literally. So it leaves us with this fascinating question. We solved the computation problem, but in doing so, we created this enormous energy problem. The next great breakthrough in AI might not come from a brilliant new algorithm. It might come from a completely new way to power this massive machine we've built. The race is on.